So my talk is about the Quarkonium in the Isr process at Belle and Belle II. Okay, so first in slide number 2, the Quarkonium states in the E annihilation experiments. So the Quarkonium has a component of a pair of heavy quark. For example, the pair of charm, pair of bottom quarks, and there's a good playground for the quark model and good playground for the exotic XYZ states. You can see in the left plot. Here I put the OU plot of the germanium and germanium-like states here. I don't put the botamonium plot here because almost all the botamonium study come from the resonance data, so they are not from the Isr analysis. You can see in this plot, many people have shown that under the DWR threshold, the series of the model and others works very well, but above the threshold, there are many exotic states observed. And in the B factory, the germanium and germanium states can be produced via the three main sources. First is from the directly B decays. The second is from the Isr process. The third is from the default annihilation. Okay, now we're in slide number 3. So there are various interpretations of the exotic states. For example, the molecular, the tetraquark, and the hydroquarkonium, also the hybrid global and pentaquark, and many other interpretations. But the high priority of these interpretations is to identify the most prominent components in wave function, and the second unique picture, which can describe all the XYZ states, not state by state. Okay, slide number 4. So for short introduction on the initial state radiation method. This method was proposed as early as 1968 by this paper showed here. And the Isr technique is very effective to study exotic Y states. Its GPC is 1 minus minus. The mechanism of the Isr allows to study the energies below the central below the designed central mass of this collider, because the photon takes some energy, and it can be compensated by the high luminosity at B factory. This method provides us a very wide energy range for the cross-section measurements. Okay, slide number 5. I'll give an overview of the results in bar collaboration. So the first observed Y states via the Isr process is the Y4260, which is reported by Barbar in 2005, which the data has the integrated luminosity of 133 bar. Then Barbar in 2017 reported another Y state near the energy of 4.3 GeV in the pi Psi2S final state, which is the Y4360. Barbar also reported the study on the cross section of the DS and DS star pairs, and here we can see 3 Psi states: Psi 4040, Psi 4560, and Psi 4415. And this study is reported with the integrated luminosity of 525 units. Okay, slide number 6 is a short introduction on the super KKB. But many people has introduced it, so just pass this slide very shortly. In the Belle 2, we have the nano beam technique, which will allow us to have a higher luminosity. And then the goal of the Belle 2 should be the 50 inverse alpha, which is 50 times more than the luminosity collected in bio. Okay, then in slide number 7, here's a summary table of all the ISR results reported by bio experiments. We can see there are around 10 Y states observed or confirmed by bio in the ISR processes. And there are also several psi states and 2 ZC states, which I will introduce in detail in later slides. Okay, slide number 8. I will introduce some remarkable germanium-like regions observed via the ISR processes. The first one is the Y4260. It was observed by Babar in the Pi Joseph states. And then in 2017, the bio experiment observed the 2 Y state, confirmed the Y4260 in the Pi G7 states, and also another observation of the Y4360 and 4660 in the Pi twice final states, with the 548 inverse quantified data. Then in 2013, Bell announced the observation of the charged tetraquark candidate, which is called ZC plus 3900. It's observed in the Pi plus G7 state in the Pi G7 process. And 2 years later, in 2015, another charged ZC state called ZC plus 4050 observed in the Pi plus Pi 2s final state, but it is only an evidence. And then in slide number 9, the latest result from in the ISR processes from the bio should be the observation of the Y4626, which is observed in the DS1 final states. Here a new method is introduced. I will give an introduction on this. Okay, so first for the event reconstruction, for the reconstruction of the DS, we reconstruct it from 6 channels, and then we require the recoil mass of the DS plus and K and SR photon should be inside the D star zero bar mass window, which is the recoil mass is showing the bottom left plot. And we can see due to the poor mass resolution, the signal is very wide. The yellow histograms from the normalized DS1 Z1 events. And then, in order to improve the mass resolution, we constrain the recoil mass to the nominal mass of the DS star 0 bar, which is from the PDG. Then the resolution has improved from around 200 MeV to only few MeV. Here you can see in the bottom left plot is the recall mass of the DS plus plus ISR photon. This recall mass distribution is after applying the mass constraint. The yellow histogram still from the set band events. Finally, the fit field has around 300 signal events with a statistical significance of 8.0 sigma. And then in slide number 11, some further study on the Y4660 state. So we can see that there are some Y states observed in several different final states, and these Y states have very similar mass and Ys. The mass is around 4.6 GeV, and the Ys are how to say around 100 MeV. I put this cross-section distributions in this slide. The bottom left plot is the for the process lambda C pi. The middle plot is the DS1. Right two plots are from the Belle and Belle for the processes e plus minus 2 pi pi psi twice. So then we perform a previously. It's not from the Belle collaboration, but I'd like to show it here in slide number 12. So we consider all the possible signals at the 4.63 GeV from the same resonance and put a simultaneous fit on the cross sections. So we get the mass and Ys listed here. And fit results are shown in right three plots. Yeah, but and I also list some theoretical interpretations on this Y state. For example, the interpretation about the tetraquark states, the molecular states, and the possibility of this to interpret it as the high Germanium. Okay, then in slide number 13. There is almost no Quarkonium study from the SR processes, and maybe this one is the most closest one. Here you can see it's the new structure observed near the 10.75 GeV. All this analysis is performed using the unresonant state of the womb signal 10860, but then the author also put the ISR data, which is in blue in the right three plot, to put the data here, and we can see that the ISR process provides some support for the new structure. There are also some interpretations for these new states. For example, the D-value Quarkonium, the bista dynamically generated pool, and hybrid, or the candidate of the tetraquark. Okay, so in slide number 14, a short introduction about the ISR study and prospects at the Belle II. So imagine if we have around 50 inverse EGBA data collected by Belle II, then the ISR analysis in Belle II should be comparable with the Belle III, which collect data in direct E plus minus conditions. And then we have the advantages in the continuum mass range to investigate the fan structures, and we have a unique advantage as well, because we can go to the higher mass region for example, greater than 5.0 GeV, which battery cannot reach. In the bottom table, list some golden channels. For example, the pi plus, the pi GSI channels, which can study the 3 byte states, the Y4048, Y4260, and the ZC, the ZC3900. Also, for some other channels listed here, I will not introduce one by one. The statistical errors are also listed in the middle columns for the data size of 10 inverse gigabyte and 50 inverse gigabyte separately. In slide number 15 is some prospects and Belle II. So I'd like to measure more precisely the line shapes of more final states in annexilations, including optimum and the germanium final states. And we can search for the Y states in more processes, such as the YK2 charmed baryon pairs, for example, the sigma pair and the lambda sigma. And the charm string emission pairs, for example, DS2, DS star, DS0. And we can also search for the ZC states decaying into the KGSI DD pair like this. And we, because given the large data set, large size of the data set, we can determine the quantum numbers, measure the iron plot of the resonant amplitude, and search for more decay modes. From the slide number 16, I will introduce some ongoing Isr analysis on Belle, since the Belle II, sorry, because Belle II is running smoothly, and we already collected some data, so some Isr study already cited. First one is a very simple analysis. We search for the GSI signal via the Isr. GSI decays to mu pair. Here we use the Fourier generator, and the polar angles of the mu tracks from the simulated signal events and the data after the efficiency corrections are shown in the bottom left plot. You can see they are in good agreement, which can validate the Fourier generator performance. The red plot is the event mass of the mu pairs with integrated luminosity of 33.8 units centibar. And slide number 17, another simple analysis. Here we search for the psi 2s signal via the Isr process. We put some simple selection criteria, and finally we see the clear Isr psi 2s signals with a low background, which are shown in red 2 plots. The upper one is for the mu channel, and the other is for the EE channel. And for the next step, we will aim to the Y4260 rediscovery. After some estimation, we would expect around 60 events per 100 image centibar. Then slide number 19. Another analysis still search for the psi 2s signal, but in the pi0 GSI final state. Here I put some plots from the single mode color samples, and in this channel, we'd like to rediscover the psi 2s at the current statistical level, and we'd like to validate the Fourier generator performance, and we can check the strategy with the well-known cross-section with the E plus minus decay to psi 2s process. And for the next step, we'd like to search for the Y4060 and some possible neutral ZC states in this final state. Okay, the last slide is slide number 19. Here we search for the twice decays to yet psi. Motivation is to rediscover the psi 4040 and the psi 4160, which are searched for in bio and are evident. So here we just prepare the analysis prime and prepare for the later large data sample. Some kinematic distributions from the signal color are shown in bottom left plot, and the eta signal also from the color is shown in the red plot. So next step, we'd like to explore the extra excited psi and possible white states in this process. Okay, slide number 20, a short summary. So the Isr physics is an interesting way to look for resonance states. This is unique to the E plus minus experiments. And the expected Belle II data sample of 15 was will provide a lot of new opportunities for Charmanian-like analysis via the Isr processes. And we can see the full frame of the Belle II data taking. And all the data samples at any energy points collected by Belle II can be used for the Isr analysis. Okay, so that's all from my side. Thank you.
Thank you very much for this overview and also future possibility at Belle II. And now we are open for questions. Christophe wants to ask a question. Please go ahead.
Well, it's more remarks than a question. I think you probably know that the Y4260 is should no longer be called Y4260 because there's a high precision BEST measurement that lowered the mass significantly down to 4230.
Yes.
If I saw your page 14 correctly.
14?
Because, yeah, there you have 4220 in the last line. That's supposedly the same state as the Y4260.
Yes.
Right? So these aren't different states, but these are the same. So that would be important to acknowledge.
Yeah, thanks for this.
Yeah, and the second comment is to page 12.
Yes.
I would just like to mention that already in 2008, we proposed that the 4660 could be a bounced molecular state of the psi prime MZF0 980.
Oh.
And if it is so, it will have it has a somewhat asymmetric line shape. So for using bright weakness is not a good idea. And later we also looked at the possible impact of lambda bar interactions, and that distorts the line shape even more. And then one could make it consistent with the lambda C bar data, but the line shape is no bright Wignerish whatsoever. Therefore, I would also here like to urge you to be careful with drawing conclusions on several states if the line shape is not very symmetric, but I'm very curious to see high statistic measurements in this mass range. Thank you very much.
Yeah. Thank you for comment.
Thank you, guys. Is there... Claudia wants to ask also something. Please go ahead.
Yes, I have only two questions on the kind of trigger that you have for ISR. Do you have all neutral trigger only also, or you have only a charged plus ISR trigger? Just to understand how much you can extend your possibilities. Can you trigger on all neutral final states?
Speaking about the triggers, I'm not so
no, that's
sorry?
It's just a curiosity that I might ask you in the afternoon discussion, if so you do not need to answer now. The other another thing that I wonder is, would you, had you considered some detecting the radiative transition from the psi to S in ISR, so that you can well determine the radiative transition from the chi C2 or whatever in a different combination of quantities. That's because that making the measuring a quantity in a different combination of in this case you would be measuring gamma E of the psi to S times the radiative transition to the chi C would strongly constrain all these transitions in a different way, basically. So you would add an orthogonal constraint to the branching fraction fit, which is performed over all available data. That's something which you have the possibility to do, basically.
Yes, okay. Thanks for the comments. But for now,
it's not really a comment. It's making a point of what you could probably do.
Yes.
If you're not measuring the individual branching fraction with a precision as good as in BEST 3, but you're measuring it in a different combination, so you're providing somehow a different constraint. You might consider it and see how much you can do with it.
Yeah, thank you for a comment.
Thank you, Claudia. I think we can continue also this in the discussion in the afternoon. Are there further comments for the speakers? If not, thank you to the speaker and to all people who participated to the short discussion.